We are talking statistical mechanics. I hope you also did your homework again today in Excel file. The homework which I'm going to assign you today is again an Excel file, which will be due on Wednesday. Very similar. We're talking about statistical mechanics. We thought we can figure out something about the nature of systems if we just sum up over their microscopic states. If we just sum up over all the different ways at the atomic level the system can be set up, multiplying whichever property we are interested in, like internal energy, with the probability that that state is occupied. And then we got to a couple of functions as shown over here. And we're going to go back to that in the second half of the class. But in the first half of the class, I'd like to do your homework so that you know what to do. And so I would like to think now about a diatomic molecule. I would like to think not about the long quadriphenyl or fluoroquadriphenyl, which we looked at so far, but now I would like to look at a simple molecule, let's say carbon monoxide, CO, diatomic molecule. What is the canonical partition function of this diatomic molecule? Now, for that to understand, I need to realize the molecule can undergo translation. It can whiz around in this room over here. And gas theory told us quite a bit about that. And we are going to get back on that, but I'm rushing to get to the next part of this one first so that we for sure have all the stuff you need for your homework. Then the molecule can rotate. If it's a diatomic molecule, it can rotate this way, can rotate that way. It cannot rotate this way because that doesn't change the molecule. And you can see the different markings. The molecule cannot rotate. So it has two ways of rotation. There are some degrees of freedom, arguably, maybe two, in it. And so there should be some energy associated with it. And then the molecule can also vibrate. That's probably for weak state. And then the molecule can also have electronic excitations. We're not really going to do this. But let us first look at rotation and then finish up all the other things. So let's first look at rotation. So if we want to look at the rotation of the molecule, we find it's quantized. And that is a real problem in this class, that on the one hand side, I'm going to teach you statistical mechanics, and that is about quantum states ultimately, but you didn't have quantum mechanics yet. At least many of you didn't have quantum mechanics yet, because you're taking the next quarter. And that is also the problem about all the books, and that's why I'm not really recommending the Atkins, or not really recommending the Levine. They all teach quantum mechanics before they teach statistical mechanics, and it makes a lot of sense if you use statistical mechanics and quantum states to do it that way, but it's just not the way you have to do it. There's no good reason for that either. It was that when UCR started its chemistry department in the 70s or so, it just took the classes from UCLA as they had at that time, and so nothing has changed in that. So in the 1970s, quantum mechanics was still something newer than it is these days, and there were some historic reasons why people first talked about statistical mechanics, and then this newfangled quantum mechanics kind of thing was coming later. It's outdated, it's reality, it's the way class is set up that we have to live with. So I have to tell you now that if I have rotation of a diatomic molecule, please believe me that there are rotational energy states, just as there are electronic energy states. Like you have the 1s, the 2s, the 2p, and so on. You have quantum numbers for the electronic state. For the rotation, there's only one relevant quantum number. The one relevant quantum number for the rotation is J. And J, like N for the electronic states, J counts from 0 to infinity. And there are the energy of a state is then derived as J times J plus 1. That are the rotational energy states multiplied by this term over here, h bar squared, over 2 times the moment of inertia of the molecule, with the moment of inertia having to do with what is the radius and how much mass is hanging at the end of the radius. Very frequently people don't write it as h bar squared over 2I, but just call the whole thing over here B. It's just the way it's done. Because B has the units of energy. And so it's better to have maybe something which has units of energy. But you can calculate from B what is the moment of inertia, and from, if you know what the masses of the atoms are, then you can also calculate from that what is the distance between the two atoms. Okay. Now, those states are degenerate, and they are degenerate by 2J plus 1. That is very similar to those quantum states, correct? The angular, the momentum quantum number runs from 0 to n or something, or n minus 1. Things like that. And it is 2J plus 1 degenerate. So, I can then just right away see what that is. Unfortunately, I don't have my laptop today. But let's do it over here for a second. So if I have this, then from this and that up there, I know right away that my Z has to be the sum over all states. But I don't really want to sum over all states. I only want to sum at this point over J, because that's what I know. And then every state J is there 2J plus 1 times, correct? That is the degeneracy of that state. So, and then that has multiplied by the energy e to the power of minus E what? But that is B, this is a minus sign, B times J plus 1. And that needs to be divided by KT. Okay, that is my J. Okay. That is my Z. Now I have my canonical partition function. It looks a little bit different because typically we would count over all states, but we realized some states are degenerate, and so rather than counting this state as 2J plus 1 times in here, I just multiply it by 2J plus 1 and just count over the J's. Does it make sense to everybody? Why we have this factor over here? Does it make sense to everybody? I'm just making my work easier in counting. Otherwise, I would need to do it harder. Otherwise, okay, good. Now, if that is the case, let's look at the carbon monoxide molecule. In the carbon monoxide molecule has this B as 1.9 times 1.9 wave numbers, or inverse centimeters. Don't get messed up with this. The wave number in inverse centimeter is the unit of energy. Yes, it is not, but it is. So people think about inverse centimeters for historic reasons as the unit of angular energy. It is like when they had the rulers and counted how many parts are there, how many lines can they make per centimeter in their grading, and then centimeter was a handy unit to count how many gratings they had in their grading, or how many whips they had in their grading, and then it came from that. So whatever the reason, inverse centimeter is a unit of energy. And so this would correspond to 0.23 millielectron volt, or 3.7 times 10 to the minus 23 joule. If you think about spectroscopy, no, inverse centimeter is called wave number, and wave number, and it is the unit of energy. Okay, with that, let's see that we can do that. Okay. So, let's get it going again so that you can see. So, what do we need to do? Now, if I want to have the Z, we had a prescription for that already. Let's have count for J, and J runs from 0 to 1, and so on and so forth. So, that are my J's. Then the degeneracy is 2 times J plus 1. So how many states with the same energy there are, that is given here. Then the energy of the state is given by the V, and we do it in joules, and I define that already as LV over here, times J times J plus 1. That gives me the energy. 0, of course, because J 0 here. But here it gets okay. Okay. So now I have the start of my table over here. So now I can worry about the temperature. And so that you can see what I'm doing. So let's worry about the temperature over here, and let's say, okay, in the temperature, I'll start maybe with 0.1 Kelvin. I'm at very low temperatures, and then this is this here times 1.3 or so. Okay, so I'm going to 24 Kelvin. So then, as the next one, I can say, okay, what is x of minus e over k t? Then that x is x of minus e over the Boltzmann constants, which are defined as a constant, times t. Okay. Now, in order to be able to pull it to the right, I need to protect that I'm always staying at the energy, so I need to protect the column up here. And in order to stay at the temperature when I pull it down, I need to protect the row over here. The nice thing about using the variable for tables is that there's no protection. Okay, very good. Good. Let's make this a little bit up.
now I can move the whole thing over to the right hand side. Okay, so now I have all of those values. Then I can try to figure out what would be Z. Now we just looked at, for Z, I need to take the sum of the product, and the product is the degeneracy, how often do I have the state, and of course the exponential term. That is what I have on the board at the moment. And that gives me Z. And it's 1 because these are also smaller than you could see. Now, in order to pull it to the right, I need to make sure that everything is protected. The degeneracy needs to be protected here, that I'm not pulling them away. And I get my rotational canonical partition function. Okay, that seems to be the first thing you might want to plot. That is not what I want to plot, sorry. And we see it's Z and so the Z stays nothing, very low in the beginning, and at about 2.5 Kelvin or so, it starts going down. Okay, then I can also try to figure out what is the internal energy of our system, U. If I want to know what is internal energy of the system, then the internal energy is, again, a sum product. And now in the sum product, I need to first put the degeneracy, how often I have the state. Then I need to have the energy of that state. And then I need to have the x value, and then I need to divide the whole thing by the normalization, the canonical partition function. That gives me the energy. Now, in order for this to all work right, I need to protect that I'm not moving out of my degeneracies, and that I'm not moving out of the energies. And I can get the internal energies. Okay, here I have the internal energies of my system. Now I would like to have a plot of that one as well. So I have the plot of Z here. I just pull it down, and I have the plot of U. Okay, they look similar, not identical, but similar. They relate to something very, very similar. Okay, U. I can also wonder what is the entropy of the system. And if I wonder what is the entropy of the system, then that was U over T. U divided by T plus K, that was LB here, times the logarithm of Z, right? That gives me the entropy of the system. You know that from here. What's this one? Okay. So we have the entropy of the system, so we can plot the entropy of the system. Okay, there's the entropy of the system. That starts already to look different than the other two. So pretty much low entropy, really low, and then at this kind of low temperature, somewhere there, it starts going really very far up. Now, as the next thing here, I would also like to plot the heat capacity of the system. What is the heat capacity and constant volume of our system? Now, we derived that. That was this thing over here, right? It was 1 over k Boltzmann times t squared, and then the difference between the average of E squared and energy, average of the energy squared and the square of the average of the energy. Okay? So, then that is the sum product of the degeneracy and the energy, and the energy again, because it's energy squared, and the exponential portion. Okay, and that needs to be divided by Z in order to be normalized perfectly. And then I need to have it minus the energy squared. The energy already I calculated, so I don't really need to do much about this one. I just need to square that. And then I need to divide the whole thing by K Boltzmann and the temperature squared. And should be fine, except that, of course, I need to protect the degeneracy here, and I need to protect the energy here, and I need to protect the energy again over here. Okay, so I have my heat capacity. Okay, that's my heat capacity. And I can plot that, of course, again. And now it starts looking kind of strange, doesn't it? So now it's looking a little bit unexpected. I hope at least it's unexpected. That we have here internal energy, the entropy, and then the heat capacity is this weird thing. They all look somewhat different, don't they? So the internal energy starts out at really low temperatures. It has practically no energy in the rotation, and then it comes up a little bit. And at the same time as it comes up, the entropy starts to increase. Because now it can occupy many states. There is disorder, if you wish, in the system. The system can be in different rotational states, not only the rotational ground state. So there's disorder in the system, and so we get entropy in that. And the heat capacity is at the same time kind of going up. And then, at some point, it overswings a little bit, and then it stays constant. The heat capacity. If you go further on, it stays constant. Now, I have artificially limited myself to the first 10 states over here in the system. I put only 10 states. In reality, J goes, of course, to infinity. But for the temperatures I looked at it, that is like 20 digits behind the zero, right? Or so. So that is beyond the precision of what Excel calculates anyway. So I'm doing good doing 10 states here only. In your homework, you'll do 8 states only. But in reality, of course, you would go maybe to more. Okay. What else can I reasonably put in my plot? How can I compare that? How does the rotational energy of my molecule, for instance, compare to the translational energy? Maybe I should add that to my graph. Let's add the translational energy to our graph. So what we had over here was really broad, right, for the rotation at the end. Let's make some room and also make the energy of the translation in here. What was the energy, internal energy of the translation? Don't need to do anything in maths of that. We know that 3/2 K Boltzmann times T, right? That was the whole thing which we did in gas theory. Internal energy just of the motion of the particles in the gas is 3/2 K Boltzmann times T. So that it equals 3/2 times K Boltzmann times the temperature. Okay, let's see, there is our graph over here, and let's select a data and add a data point, series names, is the translational energy, and the x values are the temperatures, and the y values are the ones which are the lumen. Okay. So here we have this plot now for the rotational and the translational energy. They are on the same kind of scale, and there's not much difference in the energy of the molecule in rotation and in translation. Maybe nice to know, I don't know. Then we can also look at this graph over here and see what is the heat capacity of the system for the translation. That here was really a CV for the rotation, but we can also look at CV for the translation of the molecule, because that is trivial as well. If internal energy of our system is 3/2 K Boltzmann times T, then the heat capacity is the first derivative by T of that. First derivative of 3/2 K Boltzmann times T is just 3/2 K Boltzmann. So this one here equals 3/2 times. And that is constant. So I'm looking at my rotational temperature over here. Then I can add another line, and I'm really interested in the translational now, and the x values are up here, and the y values are down here. And okay. So, if I'm looking at the heat capacity for translation, the heat capacity is up there. It's a constant value. It's a little bit larger, about 3.5 times larger than that one for the rotation. You can say, oh, there are 3 translational degrees of freedom x, y, z. There are only 2 rotational degrees of freedom for the molecule because it can't spin along its own axis. So it should only be 2 degrees of freedom, and that is 3. So this is 3.5 times as big as this. Makes some sense. So we can figure that out right away. Of course, at this point I forgot that carbon monoxide would be ice and a solid long before we reach the temperature of 5 Kelvin or so. But grant me that. Otherwise, I should have made this hydrogen then for the state gas. Helium. What else? So, yeah. That is what we can do with these graphs. And that is what we're going to do for envelopes. Now, I have a few more things where I would like to go back over here. And we haven't really done everything what we needed to do. Let's do this. And some of that will give us some more insight. So there are a couple of things which we actually want to do, which I neglected earlier. But maybe I'm staying with the rotation still for a moment. Because if we have the rotation here, then we can do it this way as I just showed, but we can do it in a different way as well. And that is that we're going over here. We know that we have this one here. But we also realized we are at really low temperatures here. We are at temperatures close to 0 Kelvin. That's usually not where we do chemistry. And so maybe our energetic spacing are really, really small. And then rather than thinking about the whole thing as a sum, we might want to think about this thing as an integral from 0 to infinity of 2j plus 1 e to the power of minus b times j times j plus 1 over k Boltzmann times t, and we are integrating over j. All those quantum states are just very small steps in energy that we are doing. If I have small enough steps, I can convert the sum to an integral. I hope that makes some sense to you. Okay, if I'm doing that one, that looks like a nasty integral over here, because now I have the square and the j over there. So I don't really want to do the integral this way. I would rather want to say, I'll take a new variable, which I call b, or anything else you like, and that is j times j plus 1. And now I would like to substitute everything over here. So then I have the integral over here of 2j plus 1. Maybe once. So in order to I need to get rid of the dj over here. So in order to get rid of the dj, I ask myself, what is dv by dj? And for that, I need to multiply this out. This is j squared. J times j is j squared. First derivative of j squared is 2j. This multiplied is j times 1. First derivative of j is 1. So dv equals 2j plus 1 times dj. So now my integral up here is 2j plus 1 dj is 2j plus 1 dj. So that gives me just a dv at the end. And then I have e to the power of b over kt times v. That's all that's left. Now if I put in the first order 0 into here, I get a 0. If I put in infinity into this formula, I get out infinity. So the boundaries haven't changed. Okay, then I can do the integration, of course. Or I can say something else in before. I can say, maybe I have a temperature here, and I have a B over K there. I can't have a unit in my exponential because e to the power of centimeter makes no sense, or whatever unit. So this one here, V over K, needs to have units of temperatures as well. So maybe I want to call this B over K. Maybe I want to call this B over K theta watt, the characteristic temperature of my rotation. So that really what I have written over there is theta watt over T, right? That's what's written over there. Okay, but I wanted to do my integral of this, and the integral of this is, of course, that I have still e to the power of theta watt over T with a minus sign in front of it, times V, and I have minus T over theta watt in front of it. If you take the first derivative of this one here, minus theta watt over T will come down, cancel with this one, and you'll get back exactly where you were. Okay? And it is in the limits from 0 to infinity. Okay, let's put in the limits. First, I need to put the top limit in, that is infinity. If I put infinity in here, then I have minus some value times infinity. E to the power of minus infinity is 0. So I have a 0 here, no matter what is in front of it. And now I put a 0 in here. E to the power of 0 is 1. I have a minus, and then that minus sign again is plus. So I worry not about any of those ones. T over theta watt. So my canonical partition function for the rotation is a really simple one. It's Z over T over theta watt. Under the assumption that I get go from the sum to the integral over here, which assumed all the energies are small. So let's see how good or not good that assumption was. So the whole thing by integral, then that what I would have over here is that I have the theta watt equals fixed Boltzmann constant divided by the value for B times the temperature. So let's see how good this approximates really is. So at really low temperatures, we are making a mistake, correct? But as we go up in temperature, they come relatively close to each other, those two values. So that's actually pretty good approximation if we are above maybe 2-3 degrees Kelvin or so. So that, what we did wasn't too big of a mistake, what we had. Okay, that's nice. Then we can of course also wonder what is the internal energy of our system. So what is the internal energy of the system? The internal energy U of the system U equals KB Boltzmann times T squared d L N Z by dt, correct? Now Z was over here. So in our simplification over here, we have equals KT squared d L N Z d L N of T over theta rod by dt. Okay, let's do the first derivative. Equals KT squared. External first derivative is 1 over that, correct? So it will be theta rod over T. And then the internal first derivative of T over theta rod is 1 over theta rod. Okay, so this cancels and that cancels and it's KT. So the internal energy is KT. So let's do that as well. Okay, so the integral one is the gray one over here, and that seems to be pretty close to the blue one. So that worked really nicely. Now we can also then, of course, see what is the heat capacity we should get from our system if we want to know what the heat capacity is. The heat capacity is here du by dt equals dkt by dt, which is of course just k. So we can also look at what is the potential heat, the heat capacity which we get from the integral and that is just the Boltzmann. And
that seems to be pretty spot on if we go to higher temperatures. So the integral really works well if we go to temperatures of above the few Kelvin, but then we are getting out. Okay. So this is exactly, now we know how far we got in class today. Make exactly the same Excel file which we just got. Make that for homework. Get us a homework. Let me say one important thing still. And that is, now typically what you would do is you would measure the bond length of carbon monoxide by means of X-ray diffraction. That way you can figure it out kind of right away. But if you didn't have X-ray diffraction, if you just measured the heat capacity, and then you were trying to find out where is the step over here, where is the step that we have here, if we started out, if we just look at this step here in more precision, we can figure out where is the step. And from that step over here, we know what is the characteristic temperature of the rotation. The characteristic temperature of the rotation, if you actually work that out over here, what we did here, is 2.4 Kelvin. So it's like here. That is like here, the characteristic temperature. So you can then get the characteristic temperature, and from the step over here, and then from the characteristic temperature you get the B, and from the B you can get the moment of inertia, and if you know the atomic masses, you can get from that the bond lengths as well. So you can actually, by looking at the step in heat capacity, measure what is the bond distance in carbon monoxide. Now that is not the practical thing for carbon monoxide, but it is very important as a technique looking at the heat capacity to see when particular states come in. When does it start, when do they start playing a role? If you were looking at, now it's a ferromagnetic to paramagnetic transition. Now you can measure that in the heat capacity. If you have a superconducting transition, you can measure that in the heat capacity. Many different transitions in the degrees of freedom that the molecule is able to use can be found in the heat capacity. So measuring heat capacity is primarily not about measuring heat capacity. It is about finding those steps and assigning those steps to different properties of the material, and then learning at which temperature do they get in. At which temperature does it transition from ferromagnetic to paramagnetic, for instance? Or is it antiferromagnetic and not ferromagnetic? Things like that. Properties of molecules can be determined from steps in the heat capacity. And for that reason, much of material science and materials chemistry is about measuring heat capacities. Okay, with that, you have your homework. We are going to talk about vibrations and other things.